Hi, everyone. Welcome to the technical session number 10, the session after the banquet, and the outrageous opinion session. I'm Cecilia Tester. I'm assistant professor from Georgia Tech in the School of Cybersecurity and Privacy and the School of Computer Science. And I'm really excited to be sharing this session on equity and how different populations experience the internet. So let's welcome our first speaker, Udit Paul. He just defended his PhD thesis last week at UCSB. Congrats. And he's currently working in the R&D and data science team at the speed test vendor Ookla. Very different from his research.
Okay, thank you everyone for attending this talk. My name is Udit Paul, and in this presentation, we will go over our research on broadband affordability using a curated data set of ISP plans in the US. So whenever we talk about internet access, the discussion needs to focus more away from just the availability, and we need to look more into the quality and affordability aspect as well. Now, whenever we talk about quality, we are particularly interested in the fundamental characteristics of the internet connection in terms of the speeds, like the upload and download speeds. And when we talk about affordability, we are referring to the cost associated with accessing internet services. Now, affordability is a big issue around the world, but even in the US, a recent study showed that about 10% of the total US households cited cost of access as the reason for not having a broadband connection at home. So even in the US, this is a big issue, and as such, we cannot just overlook this very important component that ultimately affects internet adoption. So in the US, there are currently a lot of programs, a lot of funding initiatives that is trying to tackle the issue of how to bridge the divide of digital inequity. So the most notable of this initiative is the BEAD program, which is this astounding $42 billion project that is currently underway, whose purpose is to build new infrastructure and drive this massive adoption of internet access all around US. Now the question is, what sort of data do these initiatives need to make use of so that they can ultimately achieve their objectives? Because $42 billion is a lot of money and it doesn't come around often, so we need to make sure that all the set objectives are met, and this has to be a data-driven initiative. So let's look at the data that is currently available in this space. So firstly, the access level information historically has come from the Form 477, which is published by the Federal Communication Commission in the US. This data used to be reported at the granularity of census block, which in the US demographic sense is this unit of demography that can contain about hundreds of people. Now, obviously, this was an aggregated data set. It was coarse in nature in terms of spatial granularity. So it had a lot of shortcomings in terms of hiding the underlying underlying individual samples. So to their credit, the FCC realized that we need a much more granular data set of broadband availability and quality. And to that end, end of last year, they released the new National Broadband Map. Now, this map publishes the information related to internet availability and quality at the finest spatial granularity of street addresses. So this is a fantastic data source. It's now much more granular than what Form 477 used to be. But the shortcoming is it stops at the speed level. Like, it just tells you, given the street address, what is the speed we are ending up getting. It makes no mention of how much that particular speed actually cost for people living in that street addresses. And as we saw, broadband affordability is not a small matter. It means that as much as we have, and we're grateful to have information related to availability and quality, we also actually need the information related to broadband affordability. Given that this information doesn't exist, in this work, our objective is to curate a data set that can then be used to understand broadband affordability in the US. And to do that, we need to make a tool, because the data set doesn't exist. We need to go get the data, and to do that, we need to make a tool. Now, what we rely on in this work for this particular tool are the websites different ISPs provide to their potential users. Through these websites, an user can go in, punch in the street address, and it will tell you the level of performance the ISP is promising or advertising for that street address. And most importantly, it also tells you the price associated with each of the levels of speed that the ISPs provide to that address. So we designed the Broadband Plan Querying Tool, or BQT. Fundamentally, its purpose is to mimic user interactions, just as how a regular user would interact with these websites. This particular tool does the same thing. And it takes a street address as an input and ultimately produces the speed that is available at the street address, and more importantly, the price at which each of those speeds are made available by individual ISPs. So we can see that using this tool, we can then go ahead and conduct a data collection campaign through which we can curate a data set that we then can use to answer questions related to broadband affordability. So there are certain challenges we need to overcome in order for this entire tool to produce what we call high hit rate, which basically means the proportion of queries for which we get successful responses in terms of the plans that are made available by ISPs. So across all the ISPs that we consider in this work, we come across three major types of problems that really affects the ultimate hit rate. One of them is whenever we punch in a street address, it doesn't really match the address that is stored in the ISP's backend. Another issue that we ran into was the issue of a particular street address already having an account, which means that from ISP's perspectives, they don't really advertise the plans anymore because someone already exists in that address with an account. And the final one is that of multi-dwelling unit, which are these apartment buildings. So it's a single address that has many, many units in there. And as such, the website basically prompts an error that says that this street address is not just one house, it contains many units. So we carefully study, because our objective is to essentially improve the hit rate, we carefully study each of these. How would a regular user end up bypassing these errors? And we incorporate those logics into the tool for individual ISPs. So the framework essentially becomes whenever we encounter a wrong address, we make sure that the address we inputted matches as closely as possible to the one that is currently stored in the ISP's database. When we come across the error of existing account, we end up viewing the plans as a new user as opposed to all sorts of authentication issues that comes when you want to access it as an existing user. So every single query that we made use of in this work were all viewed as a new user, so there was no authentication issue that we ever had to come across or bypass. And finally, in terms of multi-dwelling units, whenever we are presented with a whole bunch of apartment building listings, we will end up taking the one that is at random, actually, that is part of that apartment buildings. So the second option that the second problem that we run into is that of scalability, because doing data collection in this manner, mimicking user interaction, takes a lot of time. And here you can see in this CDF, for certain ISPs, for example, Spectrum, the median time it took was about 100 seconds to get one address, which means when we are trying to curate a data set of millions of addresses, this will end up taking a long time, and we don't have that much time. So we adopt the option of parallelizing that entire data collection process. We essentially containerize it using Dockers. And for every ISP that we conduct this data collection, we end up launching 100 Docker containers, which essentially amortizes the overall time it takes to collect individual street address. And not only does it make the entire process scalable, it also ensures that the process is also portable, because our objective is to also release the tool so that other people can make use of it. So this is how we ensure scalability, and at the same time, it ends up becoming portable as well. So using this tool, we curate the largest data set of broadband affordability in the US. Our data set spans about 30 cities, 27 states. The data set we make use of to get the addresses come from Zillow. And it comprises of the two of the major ISPs that provide fixed broadband services in the US. One is that, and here we can see the categories, the DSL fiber and the cable ISPs. So the next question was, how do we compare the plans? Because so many plans are provided, different ISPs provide different plans, and how do we compare the plans? So this is where we can see an example whereby this particular provider 3 different plans, and at the same time, they're priced at different amount of dollars. So we adopt a metric from the literature called the carriage value, which essentially translates to the amount of megabits per second you end up getting for every dollar you spend at that address. So in this case, this would be the individual carriage values for each of these plans. So essentially what we ended up choosing was the maximum carriage value across all the carriage values that you end up getting from different plans to denote the street address level carriage value for that particular, or CV as we are calling it, for that particular street address. Now we have conducted this analysis. We are not going to present it in the interest of time, but our analysis further revealed that at the census block group level, which is the smallest unit of demography at which census releases various demographic information, this particular metric of CV for an ISP does not vary much in the US. So to facilitate our analysis and also to conduct future analysis related to demographic, we essentially take the median of these maximum carriage values at the street address level to denote the census block group level carriage value and take the rest of the analysis forward from here. So we have answered a whole bunch of policy-related questions, but here we're going to present two of those. So one of them was, how does the competition actually end up affecting price, or the essential inherent value that a particular user get in this in the current US market? So we end up noticing that users in the US fall into one of the three categories of markets. One of them is the cable monopoly, where only a cable provider exists. They only have the option of choosing a cable provider. And then the other one is that of cable DSL duopoly, whereby a cable provider exists in that market and competes with a DSL providing operator. And the last one is the cable fiber duopoly, which, as the name suggests, the cable provider basically competes with a fiber providing, which is a much higher value providing provider. And so here we see an example of New Orleans, whereby we basically looked at how the carriage value distribution appears across all these three market types. And what we end up noticing is duopoly of DSL essentially doesn't matter at all for how cable operators price their services. So you can see the lines of cable duopoly and cable DSL duopoly and cable monopoly end up being almost the same. But whenever a cable ISP competes with a fiber ISP, it inherently increases its value by about 30%. And this is a trend we captured across all the other cities where we have done this sort of comparison, that competition does matter, and the cable ISP do end up actually increasing its value whenever it's competing with a fiber ISP. So this means fiber is very critical because it itself provides very high value, and other ISPs provide high value when they compete with a fiber provider. So one of the analysis we then further conducted was which demographic group end up getting fiber, so who gets this fiber. And for this, what we end up doing was, for every city, we essentially we pull the census block group level information of median household income, and then we group all the block groups within a city into two groups of high income and low income. And at the same time, we compute what percentage of block groups of each category gets the DSL and then gets the fiber from a DSL fiber provider. So here we see, once again, New Orleans as an example, whereby we look at the proportion of addresses for which proportion of block groups for which fiber is deployed, and we realize that high-income block groups end up getting about 16% of more high-income block group end up getting fiber compared to low-income block groups. And this particular trend was also captured across other city ISP pairings that we have considered in this work. So in the paper, we presented a bunch of other interesting results, and that further highlights and that dissects different trends related to broadband affordability. So to conclude, as we have seen, internet access is multidimensional, and broadband affordability is a very critical component of it. We didn't have, until this work, any data set of broadband affordability, and using the tool we developed, we were able to curate such a data set. We then went ahead and analyzed this particular data set to reveal various trends related to broadband affordability around the country, as well as enable answering various policy-related questions. We have also made the version of this data set publicly available so that we can drive future research in this same direction. That concludes this presentation. Thank you for listening, and if you have any questions, feel free to ask.
My name's Chris Cameron, and I'm unaffiliated. When it comes to internet affordability and access, I feel like rural populations are pretty high up there when it comes to need. And those populations are often also served by smaller ISPs that are fixed wireless. So I'm wondering, your tool that is collecting all this data, are you looking at those smaller ISPs that might exist? And then as a little add-on question, you mentioned DSL cable and fiber. But again, fixed wireless, when that enters into the mix, I imagine that could bring in competitive pressure, both because you have a smaller company that might be more service-focused, but then again, it's just like another alternative. So I guess, are you looking for those smaller ISPs? And have you looked at other internet access that brings competition? Like even in New York, I know there's the New York City Mesh. So.
Yes, that's a great question. So we are in the process of expanding this entire framework to incorporate more types of ISPs and technologies. So this was supposed to be a foundational work that sort of looks at the viability of curating a data set of this nature and then understanding if there are trends. So we are in the process of expanding it to incorporate more ISPs. So we have looked at certain rural areas, and some of these major players that appear in the city, they also do provide services in the rural areas as well. But we are actually actively expanding the scope in terms of the number of ISPs that we cover. And fixed wireless is one of those, and it's not just in rural areas, I think cities as well. A lot of cities, especially with T-Mobile being in the market, that is a major fixed wireless provider, we are sort of looking at that as well. But this all depends on whether this sort of information are made available by the ISPs. So as a primary check, we are actually looking at which ISPs can we actually integrate with our tool, and then do the subsequent data collection campaign.
Hi, Sarhat Arslan from Stanford. I don't know if this is a thing in US, but in Turkey, I'm Turkish, generally providers offer lower prices to new users for their first year or two, just to motivate churn. Is this a thing in US? And if it is, do you have any insights about how this affects the affordability?
Yes, so that is a thing here as well. So there are like promotional prices that you end up getting within first and second year. And that is actually an information that you do get through these interfaces that we ended up querying. So we have collected that information for this work. We didn't analyze that bit, but that is an information that we collect, and we'll be analyzing that as well in future.
Perfect, thank you.
Thank you.
Hi, great work. David Guzman, TU Munich. I was wondering about the pricing models. Is it possible to look at it? Did you look at it? Is it like all the same in regards of pricing models for broadband access? Thanks.
So you mean like pricing models, like how the ISPs implement the pricing itself?
Yeah.
So here we were sort of going the other way, right? So we saw the prices and we were trying to figure out what was happening. So we were looking for trends as opposed to the actual models that they were implementing, which obviously they don't make public. So that's why we were looking at, for example, our competition analysis. We were looking at how market dynamics end up affecting prices. So we feel like this is something that is hyper-localized because they are very dynamic. They do change depending on who they are competing with, what areas they are based in. So as far as the static model, I don't think any of the ISPs follow that, or at least it's not made public, and our analysis also didn't show that. So yeah, I think that essentially we are sort of trying to figure out those trends because they are not public.
Hey, hi. So Ehsan Ayub Qazi from LUMS. So I was just wondering if your analysis looks at sort of benchmarks of what is considered affordable by, for instance, the United Nations Broadband Commission, and if there are any insights at the cross-country level, across countries, that your data could bring to bear.
So we didn't do the benchmarking in relation to the actual whatever the United Nations considers as its affordability metric. So this was, once again, like I was mentioning earlier, that this is meant to be a foundational work given we were starting from the scratch. There were all these sorts of many important questions that are out there related to what we have done. But those were not all possible at that time to sort of analyze. But we will, like all the work that will build up from here, will be focused more towards that to sort of see how much, when you bring the income component to it, like what fraction of the household income is actually going into affording internet, for example. Those will be all the questions that we are now able to answer, and that's why we have made the data set public as well. So it's not just us doing the work, a lot of other people can make use of the data to answer these sort of questions.
And we'll take a last question, and in the meanwhile, if you could change your laptops.
So, yeah, Renata Teixeira from Netflix. I love this work. I was just wondering how hard it would be to extend it for other places in the world, for other countries.
So primary challenge is in terms of having an address database. So for here, we were very fortunate that we got into a partnership, a research partnership with Zillow. And then the second thing would be about having those interfaces. So we haven't done that, sort of like looked at other countries. So this is where we are hoping to be engaged with other researchers from like other countries to see whether they have similar infrastructures, and then we can go ahead and figure out how to incorporate those into what we have for US. This is not something that we have done for now, but that's definitely something very interesting thing to do.
Thank you, Udit. Great work.
Thank you.
So our next speaker is Rumaisa Habib, and she recently completed her undergrad in computer science at LUMS and in Lahore, Pakistan, and she will be starting her PhD this fall in Stanford University.
Good morning, everyone. My name is Rumaisa. I'll be presenting a framework for improving web affordability and inclusiveness. This is work that we've been doing at LUMS, and these are my wonderful co-authors. Our work primarily addresses three questions. How worldwide is access to the World Wide Web? How would stakeholders benefit from web equity? And how do we work towards equitable web access? Let's talk about that first question. And to understand it, we must address the key barriers that are limiting people from viewing the internet. And there are a bunch of them, such as digital illiteracy, censorship. But the barrier that we focus on in our work is cost of web access. This is defined by two things: broadband price, which is how much it costs a user per byte, and web page size, which is the total number of bytes that a user must buy in order to access a web page. We know that cost of access is a key barrier because of a survey conducted by the World Bank in 11 emerging countries, which showed that nearly half of their respondents had difficulty paying for their mobile data usage. This trend isn't getting any better, though. As we see an increase in the complexities of user experience, web page sizes have been on the rise, while broadband prices have remained largely stagnant. This means that each access has become more and more expensive. Access isn't equally expensive everywhere, however, as we see variations in both broadband price and web complexity. We analyzed the broadband prices in 206 countries using the ITU dataset, and we measure and analyze the web complexities of the Alexa Top 1000 sites in 99 countries, culminating in a total data set of around 72,000 web pages. Zooming into broadband price, the UN Broadband Commission considers broadband in a region to be affordable if it costs 2% or less of that region's gross national income per capita. We found that 94 countries currently do not meet that target for a 2 GB data-only plan. Moving on to web complexity, we see that in developed regions, the popular sites have an average page size of 2.64 MB, while it's higher in developing regions. It's 2.87 MB. Our data suggests that it costs more to access web pages in developing countries, considering their income levels. So to quantify affordability on both those fronts, we propose a novel fairness metric, the PAW index. And what it's essentially telling us is the reduction required in average page size in a region to equalize web accesses around the world. So a PAW of greater than 1 would indicate unaffordable access. As you can see in this graph with the red dotted line indicating a PAW of 1, a lot of developing countries don't meet this target. To be more specific, 48 out of the 96 countries in our data set have a PAW of greater than 1 for at least one data plan. So now we know that this is an issue. How would stakeholders benefit if we solved it? Let's first talk about the most obvious stakeholder, the users. Do they even want their web pages reduced? Because there exists this tussle between quality and number of accesses. If you want more accesses, you're going to have to be served a reduced, lower quality web page. So we conducted a user study with 100 participants, and in which we showed them 10 web pages with varying levels of reduction. Through this study, we found that a significant number of users actually are willing to trade off quality if it means an increased number of accesses. There, of course, exist other stakeholders, such as website operators and mobile network operators, and we believe that they also stand to benefit, as we're bringing more users online, leading to increased revenue. So now that we know that this problem exists, it matters, and that people are willing to adopt solutions, we can move on to the third and final question, which is, how do we work towards equitable web access? And here we introduce our solution framework, Affordable Web for All. AW4A transcodes pages based on both affordability and web page quality. But before we get into the details of AW4A, what went wrong with prior work? They suffered from some design flaws, such as the fact that a lot of them broke pages, rendering them completely unusable at times. A bunch of them also lacked web developer consent in a way that impacted their revenue. Facebook Free Basics violated net neutrality principles, and Google Web Live broke end-to-end encryption. So based on the weaknesses of prior work, we converged on two goals and principles. Firstly, we adapt web page sizes based on affordability, and we do this by calculating page sizes, target page sizes, using PAW. Secondly, we consider user privacy and web developer consent. And we do this by transcoding on the server side without the usage of any proxies. AW4A is essentially solving an optimization problem, which maximizes page quality given the page size constraint defined by PAW. And we define page quality as the weighted average of the individual qualities of the objects on the page. But we know that this problem is NP hard, and you can check out the proof for that in the paper, which is why we approximate a solution using a two-stage approach. In the first stage, we only consider optimizations which have no impact on quality. So this would be low-hanging fruits such as gzip compression or JavaScript minification. If the page size target has been met at this point, then well and good, we'd return a transcoded page. But we do know that a lot of pages would not reach the target at this point, so they'd move on to stage 2. Here we apply optimizations which may impact quality. And since we're impacting quality here, we want to do that in a strategic fashion. So let's zoom into stage 2. At stage 2, we design two approximation algorithms. Firstly, there's grid search, which is a naive brute force approach, which searches a discretized space of possible optimizations. This results in high-quality pages. However, it runs in exponential time, so it's not very suitable for dynamic pages that would need to be transcoded more regularly. That's why we also devised a heuristics-based approach, which results in slightly lower quality pages as compared to grid search, but it runs in linear time. So I want to give you a sneak peek into the heuristics I was talking about for HBS. We consider two heuristics for images. Firstly, there's area on the web page. As you can observe, finer details like the wrinkles on the flag tend to get lost in the smaller images, right? Which is why changes made to the smaller images would be less visible to the naked eye. So we consider that, and we also consider bytes efficiency, because some images just tend to handle reduction better. So for the same change in visual quality, some image would give you a greater bytes reduction as compared to others. So while I won't go into more details about the heuristics, I can attest to their effectiveness. In our evaluation, we found that half of the pages generated by HBS maintained a quality of 0.98 or higher. Moreover, we conducted a small-scale user study comparing against alternate solutions to reduce web page sizes, and we found that users tended to prefer HBS-generated pages over their Brave and Opera Mini counterparts. So in conclusion, we show that lack of affordability is a key barrier in accessing the web. Users are willing to trade quality for quantity of access, and there are practical solutions to improve affordability. For more details, you can contact us here, check out our source code, or check out the full paper. Thank you, and I'm open for questions.
Hi, Ari Fogel with AWS. So I'm wondering what percentage of the data is implicated in these website polls, would you say that cover is compared to users' limited capacity for download versus things like API access, email, video, other things that might be using up users' limited monthly quotas?
Yeah, so when we're talking about the sizes, we're considering all of these objects. So video would be included as well, JavaScript images. So web page sizes is going to be an accumulation of all of that.
Hi, Eddie Kohler, Harvard. Thank you so much for this. I was wondering if you had an intuition for why in developing regions web pages were bigger. Now, perhaps I didn't understand the data, but...
Yeah. So in developing and developed regions, the most accessed, most popular sites are different. So we consider the Alexa top 1,000. And as it turns out, there are a lot of like region-specific ones, for example, governmental sites that are not really optimized that well. That was how what we observed. So we have another interesting work that was presented at the web conference where we look specifically into governmental sites and that difference.
And did you find that those sites were particularly easy to optimize with this framework, or?
Yeah, so at least for governmental sites, I can say that images were heavily unoptimized, so they don't get updated to regularly, things like that, or they're using inefficient JavaScript, things like that. Yeah, that's something we noticed.
Hi, Marwan Fayed, Cloudflare. So my question, this might be a little bit of a red herring, but something I've wondered about for a long time. When it comes to the larger websites in these places, did you get a chance to look at the same website in different places around the world and how much was actually downloaded? So what I wonder is if the quality of the path to many of these places in developed regions has a higher retransmission rate and people are actually billed for the retransmissions.
Yeah, so we didn't consider transmission rate, and you're right, that's the popular sites, there were some overlaps there. So as long as the URLs were the same, the web page was the same, we would get the same page sizes because transmission rate was not something we considered.
Well, thank you so much. Great work. And if you So our next speaker is Zach Bischof from Georgia Tech, who is a research scientist in the Internet Intelligence Lab.
Yeah. Okay, good morning, everyone. Today I'll be talking about our team's work on characterizing internet outages and shutdowns. This work is a collaboration with all the folks listed here, spanning a diverse background and affiliations. So in the last few years, more than 1 billion people around the globe have been impacted by internet shutdowns. And to be clear, when I say internet shutdowns here, I am referring to instances where governments intentionally completely cut off internet access across an entire country. So despite decades of research and efforts in our community to improve the internet and its underlying infrastructure and protocols, a government deciding to simply take away the internet really takes away the effectiveness of all this research and renders the internet useless for sometimes days at a time. Furthermore, these shutdowns often occur during already tumultuous times, and shutdowns during these periods can cause a significant amount of additional stress and uncertainty in an already difficult situation. And unfortunately, recent history suggests it's unlikely that this trend is going to change anytime soon as governments are increasingly utilizing internet shutdowns. This shows the trend over the last 7 years, with as many as 40 internet shutdowns occurring in 2021. Our goal in this work is to shed light on the characteristics of the countries that utilize internet shutdowns and how these events can be distinguished from what we refer to as spontaneous outages. And this can be things like natural disasters, earthquakes, cable cuts, power outages, things like that. So, though the community is aware of internet shutdowns, previous works typically focus on a single incident or a series of shutdowns occurring in a particular country or region. In this work, however, it's the first longitudinal interdisciplinary analysis of both government-ordered shutdowns and spontaneous outages. Our analysis focuses specifically on national-scale shutdowns and outages, occurring over a period of about 3.5 years between January 1st, 2018 and August 1st, 2021. This data set, which we consider to be one of the most important contributions of the work, includes 219 shutdowns across 35 countries and 714 spontaneous outages in 150 countries. And you can get an idea of where this is based on the map in the slide. Our analysis also incorporates data from a wide variety of data sources spanning multiple disciplines. So before I dive into some of the results of our paper, I'll just briefly go over these tools as well as the data sets we used. The primary data source was IOTA, the Internet Outage Detection and Analysis tool from our lab. We use this to manually identify and record internet disruptions around the globe. This has been an ongoing kind of daily task by members of the IOTA team since January 1st, 2018. And just to give a brief overview of how IOTA works for people that aren't familiar, users of the website can identify internet disruptions in IOTA by analyzing the three signals that we have here. This includes monitoring BGP announcements, IOTA's active probing measurements, as well as data from a network telescope. So in this screenshot here, the red section shows a disruption that we observed in Sudan in late June of 2022. And you can see that all three of the signals are affected to some degree by this. Our analysis also leverages data from Access Now's Keep It On initiative. We refer to this data set as the KEO data set usually. So since 2016, Access Now has been continuing to record internet censorship events and publish this data set along with an annual report kind of summarizing the events of the previous year. This data set also includes information on the type of censorship technique involved. So this could be like a full network shutdown, throttling of connections, or blocking specific websites or applications. It also includes pointers to news on the event, like it could be related to the shutdown specifically or kind of politically what's going on in the country. It also gives details on the geographic scope of the event. So our analysis in this paper focuses specifically on the national scale events and specifically on the full network shutdown category as well. So another one of the contributions of the work is that we developed an automated process for merging both the IOTA and the KEO datasets. This is particularly useful to us because both of these datasets have their own unique advantages. Specifically with IOTA, the fact that it uses network telemetry data in near real time provides us with rather precise start and end times of the event. It also includes information, like we can use it to record spontaneous outages, which if we want to understand the characteristics of shutdowns, the outages provide us with a kind of baseline for comparison. The KEO dataset, on the other hand, allows us to identify shutdowns that are part of the same macro event. And what I mean by macro event is like during the coup in Myanmar in 2021, this was basically months of daily shutdowns occurring every day. And those are all mapped to the same event in the KEO dataset. The KEO dataset also provides us with an additional source of validation as well as pointers to news, like I mentioned previously. And also, as mentioned earlier, there's a whole bunch of other data sets that we used. This is a wide variety of things. I won't go into all of them. But it includes things like macroeconomic indicators like GDP per capita, the prevalence of broadband access. We also use indicators from the Varieties of Democracy database, which includes each country's liberal democracy score. We also use data on real-world events. We were lucky enough to find databases that had information on coups, protests, and elections. Again, we also use a variety of networking data sets. Some of these are fairly standard, but a couple that stand out were APNIC's eyeball data set, as well as the state ownership of the address space and networks in the country. So just real quickly, I'll briefly go over some of the highlights of our analysis. Be sure to check out the paper if you're interested in learning more. But in general, we found that countries with internet shutdowns and spontaneous outages tend to be more autocratic compared to countries that had neither type of event. With that said, the difference was much more stark with countries that do have shutdowns. As you can see, that distribution is pushed to the left. I think one of our most significant findings was that we found that internet shutdowns were much more likely to occur on days of political mobilization. Specifically, we found that shutdowns were much more likely to occur on days that involved protests, elections, or coups. We also note that we did not find any significant trend that spontaneous outages were any more likely to occur on these days. So this confirms previous studies and the intuition that these are indeed highly politically motivated events. And next in our analysis, we looked at the temporal aspects of shutdowns and how they compared to outages. We found that in general, for here, we're looking at the duration. Spontaneous outages actually tended to have a shorter duration overall. We also observed that the distribution for outages was much smoother compared to shutdowns, where we can see there's a concentration in a few specific bins. We kind of interpreted this as a sign of planned human actions. And then next, we also found that a similar trend with the recurrence rate, where there's a few highly concentrated bins with over a large majority occurring precisely 1, 2, 3, or 4 days after the initial event. Looking at the distribution over the start of the hour for each type of event, we found yet another similar trend, and it was much more likely that internet shutdowns were observed to start at the top of the hour in local time. Because of some half-hour offsets, we had to adjust for that. Specifically, we found that over 70% of shutdowns began at the top of the hour. In our paper, we explore the other attributes of shutdowns and outages, such as how they distribute over the course of the week and how they were visible in IOTA's dashboards. So feel free to check out the paper if you're interested in learning more about this. In conclusion, this work provides insights into the characteristics of internet shutdowns and how they compare to spontaneous outages. It also highlights the importance of continuing to collect data and conducting further analysis, which we plan to do in the future. We are also currently exploring ways to incorporate the findings of our study into IOTA's dashboards, possibly trying to make like an early warning indicator for visitors to the IOTA website. If you're interested in learning more, please check out the work. We also have tons of information on the IOTA webpage. If you're interested in using our data, it's publicly available on GitHub. The full IOTA dataset covers about 5 years almost now, coming up on the 5th year. We are also currently collaborating with Access Now to improve the accessibility of our dataset and to make it easier for researchers to incorporate this data into their analysis. So thank you for your attention, and I'd be happy to answer any questions.
Hi, Lai from Measurement Lab. I was wondering if you looked at also economic conditions throughout the course of a shutdown, so acknowledging that they're often politically motivated to start and perhaps to end as well. Thinking of instances like in the shutdown in Kazakhstan in 2022, politically motivated, but then it also sent the price of Bitcoin tumbling and or spiraling, and that was speculated to be a motivation of turning the internet back on. And so wondering if you were thinking about those factors as well throughout in terms of motivations.
That's really interesting. No, we hadn't considered it quite to that degree because like the data sets we were working with, like the economic data are generally published at the year-long scale. And so like the earlier analysis where we're looking at the distribution of countries, we actually did break that down by like a country year pair. So like Myanmar before the coup, when there were no shutdowns or outages, that's actually in the category of neither, but in the year of the coup, we used the GDP from that year and put them in the shutdowns category. But that information we didn't have at a more fine-grained granularity. But it is interesting to compare other like real-time aspects, and maybe getting it from financial markets or something like that I think could be a really interesting idea.
Hi, Ihsan Qazi from LUMS. So one question I had was that there have been several instances where the government slows down the internet rather than completely shuts down. So I was just wondering, about your perspectives of extending this data set to cases where the government actually slows down the internet. And a related question is about overt and covert shutdowns. So there have also been several cases where the shutdowns are covert, and in which case the ground truth might be affected. So I know you're piggybacking on data from other sources, but I was just wondering, when you don't have ground truth data, such as when you
sorry to interrupt. Can you repeat I didn't quite hear something might be affected? I didn't quite hear that part. I'm sorry.
Yeah, so the second question was about covert shutdowns, where it's not announced on newspapers. And there have been instances, for example, in a number of countries like Yemen and etc.
Yeah. So that is also one of the reasons why we wanted to do this study, is to possibly see, for example, we found that all the IOTA signals usually show a significant drop in shutdowns compared to spontaneous outages. And we're hoping to use this as some type of indicator for what we think is more likely for a shutdown to look like. But sorry, I'm trying to remember your first question. I kind of blanked.
Partial shutdown.
Slowdowns, yes, thank you. That is, and slowdowns is one thing as well that we're looking at right now. We're trying to see what we can do from our measurement servers to see if there's any way we can pick this up. Unfortunately, IOTA does focus specifically on complete outages, but that is something that we think will become a more utilized tool in the future, as certainly the full network shutdowns have a pretty heavy-handed economic impact on businesses, and it might make sense to block more specific applications or slow down those services in general. So that is one thing we're trying to kind of adapt for in the future.
Yeah, hi, I'm Venkat Padmanabhan from Microsoft Research India. I want to understand, what's your definition of a nationwide shutdown? Do you mean the entire country? Because if that's the case, I'd like to understand your methodology, because some of your data is not accurate. Like you had marked India, I think in the colors that said nationwide shutdown. I live there. We have never had anything close to a nationwide shutdown, right? They have been shut down in pockets. So what's your definition of a nationwide shutdown?
I guess I'd have to dig into the KEO data set, but we did actually, because I believe that's where the full country-wide shutdown is occurring for India.
It's never happened.
I'll have to dig into the data on that one. But I know that for most of our analysis, we actually had to kind of consider India separately, and we plan to look into that in the future just because of so many highly localized shutdowns that do occur there.
Alexander from ETH. Thank you for the insights. I have a small question towards the very last plot you showed, that shutdowns happen on the hour. It seems here that the random outages like the 10-minute marks.
Yeah,
is that an artifact of the data collection, or is there
Yeah,
more
that is an
behind
artifact of the data collection. The 3 different signals that IOTA has are collected at different time bins. Some of them are 5 minutes, I believe. Some are 10 minutes. And it's our methodology for, in IOTA, recording a nationwide event. It does require that we see a drop in multiple signals. So in some cases, it might be that there is a little bit of a bias towards those 10-minute increments, which we do kind of mention more detailed in the paper.
One last question.
Luke Valenta, Cloudflare. Yeah, maybe you've already answered my question, but I was wondering how you deal with false positives from certain signals, or maybe false negatives of shutdowns. So where you may see a traffic drop, but that's just sort of normal user behavior.
Yeah, so some of the signals, do have that issue, like the network telescope, for example, like just people getting offline. That does have a very strong diurnal pattern in some regions. And yeah, one way that we get around this is by requiring basically what I was saying earlier about multiple signals. It needs to show up on at least active probing or BGP, basically. And in most cases, it's actually all 3 for these. And in addition to that, whenever we do record something as a shutdown ourselves, we do kind of corroborate this with external sources. This could be from Kentic or Cloudflare. And then also using, for the KEO data set, which we incorporated, that does rely on usually kind of operators in the ground, or there are sources in the country, basically, that disclose this information. So, all right, thank you.
Thank you so much, Zach. And now our last speaker of this session is Ram.
He is a PhD candidate at the University of Michigan and a lead researcher at Sensor Planet. He is actually on the job market this year.
Thank you so much, Cecilia, for that introduction. Hey, everybody. It's good to see so many people early in the morning. Well, at least it's early for me. I'm Ram from the University of Michigan, the lead researcher at Sensor Planet. And in this joint work with researchers from EPFL, Cloudflare, and University of Maryland, we are exploring ways to detect connection tampering passively and globally. So what do we mean by connection tampering? We are referring to the restriction of application layer TCP traffic between a client and a server by a middle box that is performing deep packet inspection in the network. These middle boxes, now extensively deployed by organizations and even governments, restrict access to specific content on the internet, as opposed to the sort of complete shutdown that Zach was talking about in the previous talk. They look at specific content. And they usually restrict access to traffic by either dropping packets or injecting TCP resets. Now, obtaining a global understanding of such connection tampering is extremely important, not only to track restrictions to internet freedom, but also for helping service providers understand and explain reasons for unavailability. Now, a lot of work has gone in the past into studying connection tampering, but especially using active measurements. For years, we've built up platforms like Sensor Planet, Uni, IC Lab, Great Firewatch, all of which try to collect vantage points or volunteers in different regions, create a block list or a list of websites or content to test, and then run active measurements to these websites to understand what is blocked or what is restricted. But these active measurements are inherently limited. They're not looking at real-world user data, and thus they may miss parts of the picture, like what users are trying to access at which time. Moreover, even with the large amount of effort we've put into collecting vantage points and volunteers, it is still very, very challenging to obtain data from all networks over time. And over years of working at Sensor Planet, I can tell you that curating and maintaining block lists is an extremely challenging problem. And it is very hard to update them during times of censorship events. So in this work, we tried to look at this problem from a new way to solve these challenges. So far, the focus has been solely on the client's view of connection tampering. But the client is not the only participant in an internet connection. Maybe there's ways to look at connection tampering from the point of view of a server too, right? So we worked on the insight that these tampering signals that middle boxes would send are not only visible to the clients, but also frequently visible to the servers. And it really works to our favor that the tampering behavior of middle boxes, especially those deployed in censorship deployments that have been studied in previous work, send tampering signals or packets that a typical client application would not send. So using these insights, we built a system that can detect connection tampering from completely passive data collected by the server side. So our technique logs packets on a server as they arrive, looking for telltale signs of tampering using a set of tampering signatures. Once tampering has been detected, our system looks at the preceding packets in the connection to understand what triggered the tampering. Now imagine what such a system could do if deployed at a large cloud provider. And that's exactly what we did in deploying our system at Cloudflare, a large CDN provider that serves about 17 to 20% of popular internet domains. So a system is deployed to view a 0.01% sample of all incoming connections at Cloudflare across all of Cloudflare's points of presence. And our system is running live at the Edge network right now, but for the purpose of this talk, I'll mostly focus on a 2-week period in January 2023, where we obtained traffic from around 247 countries. I'd like to note here that we did not perform any decryption of user traffic, and we only report results in aggregate in order to protect user privacy. Okay, so how does our technique work? So when we realized that middle boxes send traffic patterns that look abnormal, we looked through the data collected by Cloudflare and combined that with insights from previous work on censorship detection to come up with a list of 19 tampering signatures, which are packet sequences that are indicative of tampering. So we create tampering signatures for different stages of an application layer TCP connection, and we use both the preceding packets and the tampering action itself to craft these signatures. So first, our post-SYN signatures identify tampering that occurs during the TCP handshake itself. Now, this is mostly due to middle boxes that perform IP address space blocking. Our post-ACK signatures detect tampering that happens during the transfer of the first data packet after the handshake. So this signature, for instance, would detect the in-path middle box system in Iran that drops the TLS client hello or the HTTP GET request. In our post-push signatures, we as the server, we would see the first data packet, but then immediately receive certain tampering signals from the middle box. And this is usually performed by on-path middle boxes, such as those deployed in the Great Firewall. And the advantage in this case is that we as the server can see exactly what the data is that triggered the tampering. And finally, we also created some signatures that detect tampering further into a TCP connection. But these are usually performed by enterprise firewalls that have visibility into encrypted traffic. OK, so the key question here is, how do we know that our signatures detect tampering? Could they just be detecting some weird client behavior? To make this distinction, we rely on certain fields in the TCP IP header, such as the IP identification or the IP ID field. So most clients follow RFC recommendations and increment the IP ID value by 1 for each consecutive packet in a connection. But so in the absence of tampering, we'd expect to see a very small IP ID difference between consecutive packets in the same connection. But most of the flows matching our tampering signatures exhibited a really large difference in the IP ID value between the reset packet and preceding packets in the connection. And this indicated that these reset packets are likely being generated by a different TCP stack belonging to a middle box. Similarly, we also found that the difference in the time to live field was also very large for flows matching our tampering signatures. OK, so now on to some findings from our global passive analysis. So the figure here, we have a few select countries in the x-axis, and the y-axis shows the percentage of flows that match each of our signatures. So we found that there is a wide variety of signature distributions across different countries. Some of these signatures were predominantly only observed from certain countries, again showing that we are detecting specific tampering behavior of a few networks. Overall, we found that around 20% of all the traffic received by Cloudflare matches one of our tampering signatures. Now, this is a really large number, which is surprising to us. And it is in part due to the fact that there are a lot of networks that perform a lot of tampering. So this is a few select networks that do a lot of tampering. But we did see a uniform rate of tampering across all networks, too. We saw that more than 80% of the connections originating from Turkmenistan matches one of our tampering signatures. But this was sort of expected since Cloudflare and other CDNs are largely blocked in Turkmenistan. We also saw significant levels of tampering in Peru and Uzbekistan, 2 countries that have not been studied by previous active measurements before. So our passive study shows that it can remove the need to find vantage points in newer countries where it may be hard to obtain. Finally, we were also able to confirm findings from previous work in China and Iran, and we were able to characterize the censorship systems there. Now, what makes me really excited about this passive study is that it can give some insight about user behavior. So, for example, we were able to look at user requests across time and found that the tampering rates that we were able to see followed a diurnal pattern. So, the tampering accounted for a larger percentage of the traffic during certain times of the day. We were able to see real-world data about censorship events. So for instance, following protests and increased censorship in Iran last September, we were able to see an order of magnitude increase in the tampering rates, and more than 30 to 40% of the connections coming to Cloudflare from Iran matches one of our tampering signatures. When we were able to see the user request, we categorized the domains in this request to understand user access patterns. That is, what categories of domains were largely blocked. For instance, we saw that around 13% of global tampering was for adult-themed domains and 18% of all the traffic from China. But we are, in fact, able to learn even more. So even though adult-themed websites only account for 18% of China's tampering, more than 50% of websites within the adult tampering category itself were blocked at least once. And this shows the sort of the completeness of the tampering system. And one of the things I really think passive measurements can contribute to active measurement platforms like Uni and SensorPlanet is help us create better test lists by augmenting information about what users are trying to access and what is getting blocked. Okay, so far today I've talked about what passive measurements can bring to the table and how it can help us in the internet freedom community study restrictions to online freedom. But we're only getting started, and we need more. So our passive signatures can be applied to any measurement data set, and we see special benefit in other large service providers and ISPs using our tampering signatures to contribute to the community's knowledge about internet freedom. Okay, so to summarize, we performed the first completely passive and global study of connection tampering. So thanks to the extensive efforts of the people on the paper, the teams at Cloudflare, and especially the Cloudflare research and radar teams, our techniques are deployed live at Cloudflare. And right now, you can go to Cloudflare Radar and see the live real-world data that we are collecting about connection tampering. Before I finish, I'd just like to announce that I'm on the job market, so if you know of any opportunities, please reach out to me. Thank you so much for listening.
That's great.
I guess I'm up first, over here. Curtis Heimerl, University of Washington. So obviously, this is a really broad set, and Cloudflare serves a large portion of the internet, but there is a bias to the kinds of applications and websites that use Cloudflare as their backend. How do you think that affects this analysis broadly?
Absolutely, that's a great question. So you're right that we are only getting the view that Cloudflare is seeing, although in some cases, we did see some requests that were two websites that are not hosted by Cloudflare. But in any case, I think Cloudflare represents a big enough part of the internet space right now for us to get a good view of what to expect in the internet as a whole. I believe this does scale linearly towards the internet. But it is sort of biased towards certain popular domains, which users are more likely to access.
Hi, Ehsan Yubgazi from LUMS. So one question I have is that you rely on the IP ID field, and there are implementations where the IP ID field is generated randomly. So I was just curious if you have a sense of the false positive rate that your study might bring in.
Absolutely. Thanks so much for the question. So we looked at what is the minimum IP ID difference between packets in the same connection. And we saw that in more than 90% of the cases, the IP ID only increases by 1. And in a few cases, the IP ID increased by a value greater than 1, but still like a really small value, which we hypothesized that these were cases where they had a global counter and not a per connection counter for the IP ID. But in a large majority of cases of connections coming to Cloudflare, we saw that the IP ID field was sort of, we can expect that the change would be small. So we believe that it's a really good indicator. There's some more details on the paper.
Udit Paul, ECSB. Great talk and great work. So I was sort of wondering, given that this paper sort of informs the players about the kind of signatures that ends up being identified, do you fear like in the future they would evolve and sort of become more complicated, which will make this sort of work more difficult? So what's your opinion on that?
That's an amazing question. So I'll answer it in two parts. So the first part is we've been working on some of these censorship systems for a while, and we've seen that they don't change very often because they're large deployments that require significant changes to both network hardware and software to change what they're doing. And I believe that even if they do change, they'll still generate newer signatures that are easier for us to detect. Like it's very hard for a sensor to completely hide what they're doing because they'd have to mimic a client exactly for us to not be able to detect them. But then that's only possible in cases where the connection is running over plain text and it's not encrypted, right? Or they'd have to have visibility into what the client is doing. So at least for the near future, we don't expect these signatures to change significantly.
Thank you.
And with that, we conclude our session. Thank you so much, Ram.
Thank you so much.
Georgia Tech is hiring in networking, so I hope you apply.